Two random variables walked into a bar. They thought they were being discrete, but I heard their chatter continuously. So, yes, we are talking about discrete random variables on the first part of this chapter. And let's go ahead and see, what am I talking about when I'm talking about a random variable? But before we do that, let's hit some games of chance and determine what's fair. So you and a friend wager on heads or tails. If he bets $1 on heads, what is a fair wager for you to make on tails? We would say a game is fair if you both come out even over the long run, no cheating and stuff like that. Since both outcomes seem equally likely, it intuitively seems fair that you bet $1 on tails. So let's do the math to check that. And so we've got $1 that you lose if heads comes up, and the probability of that is 0.5. You win $1 if tails comes up. The probability of that is 0.5. So let's just say we did 100 plays, right? What would be your expected outcome? Well, you'd expect to win half of those 100 plays, or you'd expect to lose half of those 100 plays, so you'd lose $50 on half of them. And you would expect to win half the plays, and you expect to win $50 on half of them. So you would have what's called an expected outcome of $0. And that's a fair game because you're like, oh, you might come out ahead, you might not. All right. So now you and your friend said, hey, let's take it to another level. Let's pull out the dice. And you're going to bet, you're feeling lucky, 6 is your good number, and you're going to bet $1 on rolling a 6. All right. And he's going to get the rest of the numbers. So 1 through 5 are for him. What should he be betting to make it fair? Well, I'm going to guess that you're going to say, hey, $1 bet doesn't seem fair because most of the time you're going to lose and there's no way for you to make up for on the few times that you win. So let's do some math to see what might be fair. Here I've got the table. So we've got the outcome of 1 through 5 and the payout, you lose $1 if 1 through 5 comes up because that's what you're betting, right? And so the probability of that happening is 5 out of 6. I can go ahead and say, let's assume 60 plays just to make the math easy. So you would expect to win 50 of those, lose 50 of those. That's a lot. And you're going to lose $1 every time, so you would expect to lose $50. Okay, then your winning bet, you only expect to get that 1/6 of the time, or basically 10 out of 60 plays. What should this amount be, this payout be, so that you can make up that negative $50? Well, $5 would seem like a fair bet because basically you would expect to lose 50 on the outcomes that aren't 6 and gain 50 on the outcomes that are 6. So you would come out even. So the things we've been dealing with, these are called random variables where we have the outcomes of plus $1, minus $1, plus $5. They're all random variables which are denoted by capital letters X, Y, or Z. And it doesn't have to be just X, Y, or Z. It could be anything. In fact, we'll use some other capital letters on this chapter. Now, a random variable assumes any of several different values as a result of some random event. We're initially working with discrete random variables. So they just take one value. It's like $1. It's not going to be $1.23 and some fraction of a penny. It's pretty much, it's going to be this or that. Could be $1.25. That would be allowed if you knew and could count all the outcomes. All right. Now it could be a very high countable number, but as long as you could count them. Now, if you get to continuous random variables, those, believe it or not, are uncountable. And without going into the depth of mathematics, basically, let's say you were waiting for the light to turn green, right? And you can wait anywhere from 0 seconds to 75 seconds. Because there can be fractions of a second of any size in there, it's actually uncountable, and that's called a continuous random variable. And we'll do those at the end of this chapter. Applications of random variables include games of chance. Insurance is a big application. That's how they figure out whether it's life insurance or health insurance. It's all about random variables. They're trying to figure out what to expect. Stock market also comes into play. So First of all, before we start, we always need a probability model, which is a collection of all outcomes and associated probabilities. Some common ways to display this include tables, probability histograms, and/or a formula. I like to frequently make a sample tree when I don't have the complete structure to start with, and then create my table from there. So here's an example. We're going back to the dice. We're going to a dice game where there are no points for rolling a 1, 2, or 3. 5 points for rolling a 4 or 5, and 50 points for a 6. So I basically have 3 different types of outcomes. Here's my X here, which is the points. That's really what I'm keeping track of. This is telling you what I'm getting on my die roll. But in reality, my outcome's right here. So I can either get 0 points, and that'll happen about half the time. I'll get 5 points 2 out of 6 times, or about a third of the time. I'll get 50 points 1 out of 6 times, or about 0.167. Now, notice that the probability of 6 is basically the same as probability of x equals 6, so you might see either notation. One other thing is that these probabilities must add up to 1, or there's something broken in your model. All right, so we're going to go ahead and do another probability. So this is one probability model here. I'm going to go revisit the coin flip and do a probability model for that one. Now in this one, sample trees really do help. So here we are. Here's the first flip, the second flip, and the third flip. And basically what I did is I followed each path and I counted the number of tails. So the top path had 0 tails. The almost top path, the second highest, had 1 tail. The third one had 1 tail. The fourth one had 2 tails. The fifth one had 1 tail. The sixth one had 2 tails, 2 tails, and then finally 3 tails. So I'm going to kind of combine all my zeros, all my ones, all my twos, and all my threes. So here's my table. I either have 0 tails, 1 tail, 2 tails, or 3 tails. And I basically counted, well, how many times did 0 tails occur? 1/8. And I could have said, oh, it's just one case out of 8 if these are equally probable. We know they are, but you could have also said, what's the probability of a head? A half. Head, a half. Head, a half. What's a half times a half times a half? It's an 1/8. All right. So each of these individual lines here is going to end up being an 1/8. So how many 1 tail outcomes did I have? 1, 2, 3 out of 8. So my probability is 3/8. How many 2 tail outcomes? I also had 3 out of 8, so the probability is 3/8 there. And finally, 3 tail outcomes is 1 out of 8. Now, expected value is something that we're really interested in with probability. This is basically the theoretical long-run average value. Are you going to win money or are you going to lose money? And that's a lot of what it comes down to. And it's not what will happen, it's what we expect to happen, and really over the long run, not on a particular instance. We denote it or write it as E of x, and sometimes we write it as mu when talking about the population mean. You basically find it by summing the products of the variable values and associated probabilities, and that probably went over your head. Here's the formula. You take the outcome times its probability, and then you add them up, because the probability is like the fraction of times it occurs. All right, so we're going back to our dice game, and here's my formula. And this time I added a column where I basically multiplied the x value times its probabilities. All right. Now, I could have actually done this as a fraction, said, okay, let's do something like 60 plays, because that'll work out nice. And believe it or not, I'm going to get the same answers if I had dealt with it in fractional form, or in terms of number of plays, all right? So anyways, multiplying all these probabilities out times the expected, the x value here, or the random variable, I end up with a total of 10. Now, you're probably going, wait a second, the payout's never 10. It's either 0, 5, or 50. Well, the expected value doesn't have to match an actual outcome. It's just like if you played this game 100 times, on average, you would expect to get 10 points each time you played it. You're never going to get 10 points each time you play it because it's impossible. But if you played it 100 times, you would expect to get 10 times 100 or 1,000 points. All right, we're going to go ahead and go back to the coin flip so we can do this again. So we're going to calculate expected value for our coin flip. So there's my beautiful tree that I made before, and now I'm adding a column on my table. This time I'm multiplying the number of tails times the probability. When I add these all up, I get 1.5. Now, we don't expect to get 1.5 tails when we flip a coin 3 times. You're either going to get 0, 1, 2, or 3. But if I looked at doing this experiment 100 times, I would expect to get 1.5 tails each time, or a total of 150 tails when I do the experiment 100 times. So this is what you expect to see again on average. It may not be one of these actual outcomes. Now we've done expected value, and that's pretty straightforward, all right? We also have variance and standard deviation. So basically, it's just like we did before on regression. We're going to take the squared deviation from the mean. So what does that mean? We're going to take the difference between the mean and the outcome, square it, and then multiply it by its probability. That's going to give us the variance part and add them all up. So we're going to revisit our game. And this time in this column, instead of doing probability times the outcome, the random variable, I'm taking the difference between the random variable and the mean, which we said was 10, the expected value, and I'm going to square that. So 0 minus 10 is negative 10. When I square it, I get 100. 100 times 0.5 is 50. I'll do the same thing for the next one. 5 minus 10 is negative 5. I square that. I get 25 times basically a third. Gives me 8.325, roughly. All right. We've got 50 minus 10, that's 40. Square it and divide by 6 or multiply by 1/6, and I get almost 300, 267 roughly. When I add all of these things together, I pretty much get 325 as the variance. So here's the formula for the variance if you want to refer to it. And to find the standard deviation, what you're going to do is take the square root of the variance, and in this case, we'll get 18.03 as a variance. Let's go back to my coin toss again. So now we're going to do variance and standard deviation. So again, take the expected outcome was 1.5 tails. So 0 minus 1.5 is negative 1.5. Square that. You're going to get 2.25 times this. I'm going to assume your calculator's doing the work for you, which gives you this number. So you can go back and double check each one of these, see if these make sense. 3 minus 1.5 is 1.5 squared. 2.25 times 1.125 should give me that number. When I add all these values up, I get 0.75. That's the variance. Most times I'm more interested in the standard deviation, which is the square root of the variance. But I have some good news for you. Your calculator will do this. So how do we do it? First of all, you're going to create a list L1 for the outcomes. All right. So you go in Stat and Edit, just like we did before. And here I'm doing the tails example, 0, 1, 2, or 3. So I just covered those answers, right? And then I put in the probabilities in list 2 for each of those outcomes. So they should line up. 0.12, so I got 1/8, 3/8, 3/8, and 1/8. All right, after I do that, go ahead and press Stat, Calc, and one var stats. All right, you're going to press second list and get your outcomes first, then do a comma, and then do the probabilities, and then press enter. And you see that you're going to get this outcome right here. It's calculating the standard deviation for you and the expected value. Be careful, the calculator uses X bar instead of mu. So my expected value is up here. It is using this, which is what it should use when calculating it this way. All right,